2, 1, welcome in. Speed and velocity. So this is with regards to physics. So we're going to talk about these items here. So the average speed, most of the time people just say that it's speed, and average velocity. And again, most of the time it's just referred to as velocity. So the definitions here, when you're walking into kind of grade 11 physics, are relatively simple, especially if you remember your slopes from grades 9 or 10. But even if you don't, then the definitions themselves are based on just two quantities, which is really kind of your distance and your time, okay, or more specifically for velocity, your position, okay, with respect to time. So let's take a look at these, and I'll try to explain these intuitively to you so that you can kind of see what that actual definition is. And then of course calculating it, it shouldn't be as big of an issue for you, especially if you have understood the differences between distance, position, and also displacement. Okay, and I'll put up a link up above there to that. So let's jump right in. So first, your average speed that you would have. So the actual formula for this, okay, is given here, where you have the average speed. Notice that for speed, we still are referring to the acronym for it. It's just with a V. So the shorthand is V instead of the S, which most of the time sometimes people might try to use, but in physics we try to be using the V itself. And then if we want to know the vector, as you know, we put the little arrow right above it. Okay, so the difference here that you see is speed is V, okay, and if you want velocity, then you're going to see this little vector right above it. So if I take this, and I'm going to try to paste it in here. So if this is my definition of speed, so what does this mean? Well, so first of all, what speed is referring to is something that you are commonly are aware of, especially if you've done any driving, walking, running, or anything of that nature. All you're referring to is, how far, okay, you actually go in terms of distance, and then how long it has taken you, right? So it is the division of one over the other. And that is just telling you with respect to time, how quickly you are moving along. So if I would draw here, okay, a kind of a number line in here, so let's, make this, okay, with a direction, okay, maybe east, okay, for the moment. Let's put a reference, okay, of 0. And I started to, walk around, and it doesn't really matter where I start, okay, and we'll assume that we have these, okay, are in meters, right? So the actual distance itself is in meters. So we can say that, we're at a particular position, okay, in here. So maybe we did end up starting, okay, at our reference of 0 right here. And then we walked along, okay, and then we got to a certain point. So right here, we can of course find out what the position is. Right now, if you recall, the position, okay, would have had a little vector symbol up above it, okay, and if this is in meters, this would have been 1, 2, 3, 4, and 5 meters. So the position would have been 5 meters that we have, and we're on the east side here, so that would have been our position. But in terms of the distance that we've covered, right, so if we started from right here, which was our initial distance, and then we walked all the way over there, which was our final distance, okay, right there. So this particular distance that we would have is, well, this is referring to the total distance, okay, that we've walked. So this is the total distance, let's say, walked, okay, that we had. And then here we would have just said this is 5 meters. We don't need a direction here because we're just talking about the distance itself and not the actual position. So that's what this is referring to. And now, how long has it taken us? And this is, your delta t, okay, which also, it really means your final time minus your initial time, okay, that you have in there. But most of the time, okay, as you may know, your initial time that you have right there, okay, is going to be starting from 0, because when you hit your clock, okay, right away in terms of your timer, you're going to be starting from 0, and then you're just asking, okay, so how long have you walked for? And let's say in this case, maybe we have walked this, we're walking very slowly. Okay, so maybe it took us 10 seconds in total. Now, in 10 seconds, okay, so time is not a vector for us. Okay, so in this case, it's just a scalar. And therefore, we would have that the average speed, okay, that we would have is 5 meters. So that's the total distance, okay, over the 10 seconds. Okay, and then this would have been 0.5. And notice we get meters per second in here. Now, your speed is always going to have a unit. Now, there's many units, okay, for this. But what you notice is it's a combination of a unit for distance and a combination of a unit for time. So meters per second turns out to be actually our metric SI standard. So this is the standard that we typically use in sciences on the metric side or the SI side. So we would kind of say that this is the SI unit, which is meters per second. Now, of course, you can measure speed, okay, in kilometers per hour. Okay, so that is not necessarily an SI kind of metric standard unit. It is a metric unit, okay, but it's not the standard unit. So we do have one standard, which is meters per second. So be careful when you're doing your questions, just so that you're consistent in whatever unit that they want. If they want the standard unit, then keep everything in meters and seconds. But if they don't, then you can choose whatever it is. And of course, your distances don't necessarily have to be covered in kilometers. Maybe they're in feet or miles. So of course that will depend, but with unit conversions that you do, okay, and your comfortable unit conversions, you can always go back to the metric standard. I can put up a link up above there for the unit conversions, okay, so just that you should be aware of. So coming back to this, speed is relatively simple. It's just, okay, how much distance we cover, okay, and in how long it has taken us. We could care less about the direction at all. So if you had, and maybe you've walked along in here, and let's say you started over here, you got to over there, okay, and then, you continued back, and let's say maybe you've walked all the way over here because you're maybe going and, shopping to one shop and shopping to another, although I guess it wouldn't be in meters because that would be very close there for you. But maybe you've walked and, grabbed a wrench from one side and then you grabbed, okay, a bucket from another. So if you've walked here 5 meters, and of course, this would have been going east, okay, and then you've walked, okay, so all the way on the other side, and so right here, so you would have ended up all the way on the other side there. So this is, okay, now going to be, 1, 2, 3, 4, 5, okay, but it's on the negative side in here. Okay, so if we were going in this direction, or it's positive in the west direction, so that particular negative, but in total, notice that, the 5, well, this would have been actually 10 meters in total. So if you wanted to know, okay, what your speed was, your average speed for that instance, then you would have said, okay, well, I've walked 5 plus the 10 meters in total that I had, and, how long has this taken me? Okay, maybe now you started to really speed up and you started to move along, okay, and this has taken you some time. Well, let's say that this was maybe 30 seconds. So within here, this would have been 15 meters divided by your 30 seconds, okay, and of course this would have been again 0.5 if you put in your calculator in meters per second. So that's what speed is. So speed is just measuring. It is a scalar, and this is something that we should be aware of. So there's really no direction to it. So we're just interested in measuring, how quickly we're moving along. So now that we know that, how does that differ from velocity, which a lot of people may confuse with? So it seems that actually everything is more or less the same. So notice, it has an SI unit, so the standard unit is meters per second, but it does have this concept of a vector. So if I take this now, and I really take a closer look at what this is saying, and I'm going to be comparing it to what I have just done. So this is going to be for your average velocity. So the first thing you should notice, now people sometimes get lazy, me included, but we should have a vector symbol in here. And what makes it a vector symbol is that we have a vector in here. So the denominator doesn't change. This is still just measuring the total amount of time that something has taken. But this right here, so the symbol for the delta, d, okay, this time this does matter for us because it is actually measuring the total displacement that you have. Now sometimes the total displacement, you might have a little t as a subscript, okay, within there. And what that change actually is referring to is that it is now the change in position. So it is your final position, your position maybe sometimes it's 2, okay, minus your initial position that you had, and that is the actual change, okay, and these are positions now. So both of these that you have in here, these are actual positions and no longer kind of the total distances that you covered in the case of speed, right? So how would that differ now? So, how would your calculation change? Well, your first calculation actually wouldn't be any different. So the first one, because you are starting from a reference of 0. And what I'm referring to is this. If you start from here and you walk along all the way over here, right, and you want to be covering, and you know that that has taken you, let's say, 10 seconds, okay, that you are going through here, well, in that case, what you would do is, if you wanted to find the average velocity for that instant, this would have been, now the average velocity is equal to, and now we would take our final position. Now we have to be careful in here because our final position was 5 meters. We do have to take now the actual direction, minus, so it is a vector that we're going to be working with, minus, but we're starting at 0, right? So now 0 doesn't necessarily need a direction, okay, within here. So now there is actually a 0 vector, but, okay, 0 just means that we're stuck at our reference point. And then if we would divide this, we still are dividing by the total time. And if this has taken us, the 10 seconds, then you will notice that this is still 0.5 meters, because it's the 5 and the 10, so you're just dividing that. This direction stays, right? So this is going to be in that direction because indeed we were kind of moving in this direction. So what this is telling us is that we are now traveling, okay, half a meter every single second, on average, going east, right? So this is the vector. So now you might say, well, that seems very simple and it looks exactly the same over here. But this, okay, makes it a big difference. Now, notice where it will start to make a difference, because if we now take, and so within here, so if we start over here, and now we're going to be, moving along, and we're starting to talk about the actual average, and maybe now our trip, okay, as we're going through here. So maybe we've walked all the way over here, right? We stopped, okay, and then we kind of went all the way over there. And, so maybe now what we're going to be doing is, so that this portion took us 10 seconds, okay, in here. And then the other portion, so the 10 meters going back, okay, within here. So, let's say that it has taken us, 20 seconds, okay, so going back in this direction. And that would equal the 30 seconds that I have chosen for my speed over here. So notice what's going to happen here as you are trying to define, okay, this, which is your average velocity. Your average velocity now, all of a sudden, becomes much different because you're going to take your final, so notice this is your final right there, position that you have. And that final position, so if you're going all the way over there, so it is, okay, either -5 meters east, right? So that's a negative vector there. Or you can say it's 5 meters west, doesn't matter. So I'm going to just keep it 5 meters west for the moment. And then your initial that you had right there, well, initially you were starting from 0. So it's almost like you're completely bypassing this. But of course, it's the displacement that we're interested in. So that shouldn't surprise you, because the displacement, once you remember what displacement is, really is just going to be this vector right here. So it's really from here to here. So this is going to be now all over. You need your total time at the bottom. So it was 10 plus the 20 or the 30 seconds. Okay, and in here you notice that, oh, well, that's interesting. So this is going to be 5 or all over 30 seconds, okay, west. Or you can, of course, write this as negative, right? Now, 5 over 30, if you wanted to, I'm just going to leave it as a fraction. So notice that 5 goes into 30, right? So this goes 6 times into it. So this is going to be 1 over 6, or you can put it as a decimal. And it is meters per second. And if you put negative, then that means you're doing it with respect to the positive vector, right? Which is the east side, positive direction. So that is much different, okay, than when you were doing it for the actual scalar representation of speed. So there is a difference between your speed, okay, and your velocity. Velocity is always interested in the displacement, okay, that you have, and it also carries a particular direction, okay, that you would be going into. So be careful when you do that. All right, so those are the two definitions of speed and velocity. So definitely a big difference between them on the vector side. Now, in here, there's a few things, okay, that we have. One of the things, which actually I'll mention right here, and that is when you're moving and you're going at a particular speed, you're obviously, okay, in motion. So you have a movement in terms of motion. Now there's two types of motion when you're referring to speeds or velocities. You might have a uniform speed or velocity, or you might have a non-uniform speed or velocity. So when you're talking about velocities in general, now what's the difference between uniform and non-uniform? Well, another word that is very often used for uniform, it is the word constant, which means it does not change. So there's no change in your velocity. And here, now what can possibly change? And if it does change, so constant means no change. Okay, and uniform means that it does change. And now the question arises, well, what can actually change in your velocity? Well, what can change is you can speed up, right? You can start going faster, which would mean that you are no longer moving at a constant or at a uniform velocity because you're speeding up, so it's no longer constant or uniform. Well, you can also slow down. So if you're already moving, maybe you can slow down. And that would again be, so if you're slowing down, that means you're not going at a constant speed. So it means the speed, okay, or velocity is indeed changing. Now the last one, which is interesting, you may be going at the same speed, but you are changing direction. So you might be changing your direction from east, you slowly start to move somewhere else. And that, okay, has an impact on your velocity. Because if we say your velocity is uniform, that means your speed is the same and you're also moving, okay, in a particular direction. So that's what happens. If you change it in any way, okay, then during that change, okay, it was actually non-uniform. So technically, when we were doing this example and we walked one way and then we changed our direction to go another way, right? So during that change, it was non-uniform. Now the rest was actually uniform, but we were only interested in the averages. So here, this, okay, means that if you change your direction, then that creates a non-uniform velocity. So speeding up, slowing down, or changing direction means that your velocity is non-uniform. It is changing. Now, if none of these things are happening, then you're at a constant uniform velocity. Or maybe you're just at rest, meaning that you're just not doing anything, right? So then that would mean there's no change. So that is referring to the motions that can occur. Now, for here, at least in this video, we're just going to be assuming on the average side that we're kind of dealing with this uniform, constant, okay, flow. So, as I kind of scroll up here, one interesting, very interesting item is when you start to take on physics, you are going to have these position time graphs. Now, position just means, where you are located, and time means, the time that has passed by. And from these position time graphs, the slope, so dating you back to grade 9 and 10, okay, your slope, which is kind of the steepness of your line, okay, on a graph, is actually equal to your velocity. Here I put your question mark over here, but it is actually equal to that, okay, if you do have a direction. If there's no direction, then you're just talking about speed. So let's take a look at these and try to see, what do they mean. So I've kind of prepared here on the side. So you have kind of different types of these position time graphs. So notice that on the x-axis, so we have our time right here. Now this time, typically, so you're going to have it in some kind of a unit. Let's just assume that all of them are in seconds. Okay, so it doesn't really matter for us. On the vertical, you have, okay, so on the y-axis right there, you have your position. So notice it is a position, and it is with respect to east. So, and it's going up. So this right here would mean that this is 0, and as you're going up, this means positive. So that means you're actually going, and you are on the positive side. And then here, so going in this direction would actually mean you're going in the negative east, which means you're on the west side. So if you visualize this for yourself, so if you had an actual movement that was going east and west, so this is east, right? If this is your 0 right here, this is your reference point. Now what you can see is that as time passes by, so maybe this is in seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. Notice that your position, okay, that you have, so maybe it is 1, maybe it's at 2 over here, so 2 meters. Well, at 0 time, it's at 2 meters. At 1 second, it's at 2 meters, and 3 seconds, and 4 seconds, and so on. And then it ends. So what that means is that if you tried to transfer this on here, well, if this was 2, let's say this is 1, and this is so 1 meter and 2 meters. So this means that you're stuck, okay, at this position. So you are actually just sitting here. Now, how long have you been sitting here? Well, you've been sitting here for, so you can check, this is 1 second, 2 seconds, 3 seconds, 4 seconds. So that means, okay, that you have, because this is just your position right here, that means you're just stuck at 2. Now, the graph, the position graph on the right hand side, so over here, so if we assume again it's in seconds and meters, notice that here, okay, what it's showing us, it's on the negative, and let's assume that it's 1, okay, and then maybe -2. Now what does that mean? Well, -2, you can say that this is the opposite, so you can count these in negatives if you're referring to east side, or if you want it to be on the west, right? So then that would have been you're stuck at 2 meters on the west of the reference point. So, and again, in here, as you're walking along, you're noticing, oh, well, I'm not moving anywhere. As time keeps passing by, so as time keeps passing by, I'm just stuck at the same position again. So here, over here, how long have you been sitting there? Again, it looks like for, 4 seconds approximately. So these time graphs just tells us, as time keeps passing by, where your position is. Where are you? What is moving? What's happening here? Now, if you look at over here, so this is interesting because now you're not stuck at a position. You are actually moving. So now I'm going to kind of just shift this out. Okay, let's maybe bring it over here, and I'm going to move it. So just we have it, okay, in some particular way. You will notice that right here, oh, well, it looks like I'm moving as time keeps ticking by. So notice 1 second, 2 seconds, 3 seconds, 4 seconds. Now, I can read this out more or less, right? So for instance, at 1 second over here, I'm stuck over there. At 2 seconds, I'm moving here. It looks like I am moving, okay, as you're moving along and as time keeps passing. So 1, 2, 3, 4 seconds. This is all in seconds. And then where am I moving? Notice that it's on the positive side, and we made east positive. So if I again go back over here, so to this particular chart, I'm going to just kind of remove these out in here. Okay, and we can label this. We're going to be moving in this direction. So if you were stuck here, so let's say, you started over here. Now, what you're going to be moving along with, okay, so as you have this particular item. So this thing, okay, as you have, at 1 second, so it looks like, well, it's not exactly at 1 meter, it's just below, but that means it's moving. It's moving in this direction, okay, and then it keeps going, okay, keeps going, right? So, and it looks like it reaches 3 after 4 seconds, right? So it's just moving along in this. So if you would be observing this ball, it would have been just shifting there. Now, we don't have and we don't know what happens afterwards, but this is moving. And now, how I mentioned uniform, right? So is it moving at a constant speed? Well, it turns out that if this is a line, and if it's a straight line right here, then we know that the actual velocity is constant. So it's not speeding up or slowing down, right? Okay, it's not really changing directions for us. It's going kind of constantly east. And the slope, and if you recall what the slope is, so slope, which is the rise over the run, and I can put up a link up above there, kind of refresh you on the slope if you have forgotten it. So now, with this particular slope, the rise is the change in the position, and then the run, notice it's just the change in time. Okay, so that's what you have in here. So, this is what is the change in time. So 4 seconds went by, and this is the rise, means what has happened, okay, to the position, so the change in position. So your slope actually can read off what your velocity is, and then you can just check what direction you are moving to. Now, in this particular case, so what you have over here, it looks like it's coming down, right? So if I take this, let's say, we started, okay, over here, and then maybe we ended over here. So we're going to be moving along. This is going to be from 1 second. This is 2 seconds, 3 seconds. This is 4 seconds. So if we start from here and we're going over here, so it looks like, if you're thinking about where are you starting, so notice this would have been up, so 1, 2, 3. So you started at 3 meters, and then it looks like you're moving down, right? And this is coming down. So eventually here it looks like it's at 2 meters, and then over here it looks like you're at 1 meter. Oh, okay. So if you're at 1 meter, you went from 3 meters to 1 meter. So what you have done is you went from 3 and you went to 1 over here. So notice that where are you moving? You're going west, or you're going in the negative direction of east, right? So you're going the opposite of this. And here, the slope itself, because it's slanted down, it would have a negative slope. And it is constant, so notice it's a straight line. And if it's a straight line, again, we can refer to the rise over run, and notice the actual change in between your position and your time. So this is a really nice example, okay, within here that you have of how you can take these position time graphs. And you notice that your slope tells you your velocity. So with that, okay, I want to just show you this particular example, and you can walk through this and you can say and challenge yourself, okay, you know, what's happening here? Notice we have a position in meters, we have a time that keeps going. Now, what would this mean as you're going through? Well, you started from a reference of 0, and now notice that you're going at a constant speed, okay, over here for 2 seconds, and you get to a position of 20. So if you were going, and notice it's going east, so you would have walked, all right, so walked, ran, or whatever. So in 2 seconds, you know, you've gotten to the position of 20. And then it looks like, so from this point to this point, so for, you know, a few seconds, it looks like you're resting. You're not moving anywhere. The position is constantly 20. So you're just sitting there, right? For, in this case, for 3 seconds. And then you decide, okay, well, let me go back. Notice that now it's in the negative side, so now you're going through. You pass this point, so after 7 seconds, you're over here, which is the position of 0. And then you go on the negative side, which really means now you've gotten and moved to the west. Now, how far have you moved? It looks like it's 1 spot over, so this is going to be minus 10 east or 10 meters west. And again, now you've rested because this is constant. And then again, you start to move from this point to this point. So you start now going back in and you're going east, right? So you're going in that direction. And you can find what these slopes are. And the slopes are going to tell you what the velocity is, okay, with respect to the east position. So here it's a positive slope from here to here. Here it's a negative slope, which means that you're moving in the negative direction, so negative east, which means west. And here it's a positive slope again, so you're moving in the positive direction, which for us means east, at least from this position graph. So those are pretty nice examples to be able to understand these velocities in a visual form and what's happening. So that's the introduction, all right, to these. Okay, this is what we have. So now you should differentiate between speed and velocity and start to slowly understand position time graphs and how to read them and tie them into slope. Thanks for watching. See you in a future video. Bye, everybody.